Okay, so today we're going to try to unravel a little bit more the patterns that we saw in the last lecture. So we had these simulations of point sources emitting waves. So this particular simulation is a line of point sources along the left edge. So there's, I think, 20 point sources along that edge between here and there. Okay, so this is approaching something like having an opening and the waves coming from this side, striking that opening and coming through. In fact, it looks very much like what we saw before when we were starting ray optics. Now the advantage is we know how to deal with point sources. So again, I'm going to show you first the average intensity here. So the same sort of pattern. You see again that we're getting this pattern here where there's these nulls kind of radiating out like this. And in between, there's maximums. So this is the pattern we're going to try to unravel today. Okay, it comes out a little more clearly when you take away the waving part and just look at the intensity. Okay, so like I said before, along the edge here, there's this sequence of point sources. Now we know the way to deal with that is if there's some point over here, we find the distance, and then at this point we know that we'll have an electric field, which is the amplitude from that source, and then the phase. Okay, but then we have to do it for the other ones too. So we'd have to have a different distance because it's not the same distance away. So then we'd have to add to that the next ones. Okay, so let's write that out. So the idea is we're using the superposition of electromagnetic fields. We know how to calculate each of the electric fields that arrive at this observation point from each of the sources. So to get the total electric field, we just add them up. Now one thing I'm going to do here is I'm going to assume that the amplitude that comes from this is proportional to how much of the space it takes up. So if the opening is width A and there's 10 sources in it, then the strength from that should be that distance over 10. Okay, so there'd be some other proportionality constants in there. Okay, so that's this amount of electric field coming from the first source. So then we'd add that in the next one. And so on, down to the last one. So we could write that out. A little more succinctly like this. Now, if we take the limit that we keep adding more and more of these, so not 10, but 20, 30, 1,000, the same form would happen, but this becomes an integral. I'm just arbitrarily taking a coordinate system here. That's the x direction, this is the 0. And that's the angle to the source. So I call this R0. and the distance of a particular force is a distance x above there. Okay, with this assumption, we can then, so we're going to call this arbitrary one r of x, so it depends on x. A bit of trig could find it for you. So now we're going to have dx, which is the distance between our spacing. If you think of this a over 10, right? That's our dx times the cosine Okay, so this is the limit as n goes to infinity. Okay, if we take another limit and we assume that this distance r is much, much greater than the width of the sources, then the geometry gets simpler. And we can calculate r of x. So it's r0 minus x sine theta. I won't belabor exactly why, because we're going to look at it again in a simpler case. I'll just quickly, this little piece here is how much this path is shorter than r0. And if you look at this triangle here, you can see that's, since this length is x, this side is x sine theta. Okay, so that's actually something that can be integrated. We won't bother to do it here, but it's something you could do pretty quickly, or not quickly, but you could do it with intro calculus, because it's just the integral of a cosine. It looks bad because there's this sine theta, but sine theta is just a constant. All right, so if we do that, and then we calculate the intensity, which is 1/2, oh yeah, don't forget, this is only true if we're far away from the source, so the distance from the source is big compared with the size of the opening, which is not hard to achieve. If this is a fraction of a millimeter, you don't have to be very far away. Okay, and we know how to calculate this. We take the time average of the electric field squared and multiplied by 1/2 the speed of light times epsilon naught. Okay, so if you do this integral, you'll find it's going to be a constant times the sinc squared of pi a, the slit opening width, divided by the wavelength times the sine of the angle. Again, that's something you could definitely do if you took an hour or half an hour and just worked it out. All right, you may not be familiar with the sinc function. The sinc function is the sine of x divided by x. The basic pattern is that the sinc gives you zeros. Oh shoot. At all the multiples of pi. Okay, because the sine is 0 anytime x is a pi. There is one exception at the center. If you look at you have the limit as x goes to 0 is 0 over 0. So you have to use L'Hopital's rule to find what the limit is, and it ends up being 1. Basically because for small angles, sine x is just x. Okay, but you can see it here in the graph. At x equals 0, the sinc is 1. Okay, so the basic pattern is this wiggly thing that gets smaller and smaller as you go out. What we actually have for the intensity is the square of the sink, and it actually drops off very quickly compared with this peak at 1. The next lump is very small, and you can barely see the next ones. They're really, really tiny. In order to see them better, it's often that you put that on a semi-log graph. So on the axis over here, it goes from 1 down to 1,000th. So you see this is a 10th, 100th, 1,000th. Okay, so indeed, that's what I showed you in these graphs here, was the log of the intensity in order to be able to see those small structures. Okay, so here is that same thing again. Let's see, wait a minute. But I've zoomed out a lot. So in this case, we've just got 20 here. And remember, this is our distance, R, compared with the opening, which was 5. So 20 is really not much more than 5. So this equation that we have in terms of the sink wouldn't work in that case. Okay, so again, in order for this nice thing to work here, we need to be far away. Okay. Say 100 times farther away. All right, so this graph is in that limit, or up to something like 1,000. So, and this is in units of the wavelength, so the slit opening is 5 times the wavelength, and we're out here at 1,000 times the wavelength away. So it should be fine there. And so this is the pattern we see. In addition, see where the dotted red line is here. I've drawn what this graph here is the intensity along that line. So if we just follow along here, that's finding the intensity along there. And again, it's using a log scale. And then over on the far right here is an actual photograph of light, a green laser passing through a slit. Your lab, this first part of this week's lab is going to be to analyze this image. Okay, so that's the single slit. It's this equation here. So that equation drives the single slit. We'll see some simplifications of it later. Okay, so what if you took 2 of those slits and put them fairly close to each other? All right. So here's one slit, there's the other slit. Now, imagine that they're happening here, and I've shrunk them down so they're actually very small. You can't really see them. So it's a fraction of a millimeter, the distance d. So maybe it's 1/4 of a millimeter is d, and a is 100th of a millimeter, something like that. And so we wouldn't really see them. I made a little gap there, but you probably wouldn't see them. They'd be very small. And then I've got an observation screen over here. So right now what I have is that same single slit pattern. So if you, for example, blocked one of them, you get a pattern like that. If you unblock that one and then block the other one, the pattern would shift up a little bit, but only very little bit because the 2 slits are actually really close together. So you probably wouldn't notice the change. So no matter which slit, if I had like a slide here and I could move this up and down and always have just one slit open, I wouldn't be able to see any difference from one to the other. Now the strange thing is what happens when I open both of them. Now with a normal light source, if you turn on a light bulb, then you turn on another light bulb, everything gets brighter. But that's not what happens here. You don't get the same pattern again. What you get is this thing. Okay, so you can sort of see the lumpy single slit pattern is still there. Okay, hopefully you can see that it's the same. I had to kind of align it by hand, so this isn't perfect. Okay, so that lumpy pattern is still there, but there's an additional lumpy pattern, underneath. Okay, so we see, hopefully you see this, there's all these little lumps. Okay, so inside that big central lump, there's a bunch of little lumps. Looks like teeth or something. Okay, so this is a photograph I took in the lab. What you would have done yourself if we were still in school. All right, now, again, so I think the startling thing here is these dark spots here. Why is it that it's dark there? If we open one slit, it would have been bright. If we open the other slit, it would have been bright. So why is it dark now? Okay, and we know why though. Yeah. Let's go back over to this picture here where it's big enough to be able to see. So suppose we have a point over here, and we have waves coming over from here, and we have waves coming over from there. Okay. Now, there's going to be an oscillation, a wave coming here, right? And so it's going to be this one, this source will be trying to cause the electric field here to increase and decrease. This one will be doing the same thing, increasing to decreasing. But they might not be telling it to increase and decrease at the same time. And these dark places, indeed, are the places where they're telling it exactly the opposite. So when one is saying you should be getting more up, the other one's saying you should get more down, and the sum of the two is 0. So that's what the interference comes from. The interference patterns like this, where you get light and dark places, is very characteristic of waves. You only get that kind of behavior when there's waves. This is sometimes the reason that your cell phone gets dropped, or if you're in the house and the Wi-Fi seems to be really weak at a particular spot. There can be multiple paths from the Wi-Fi antenna to your computer, and those two paths might be interfering destructively. Okay, so this pattern here looks quite a bit more complicated than the single slit, but it's composed of 2 parts. Here's the single slit. It's still there, but it's multiplied by a second term here. Okay. But it's not so much worse, I guess. Now, in practice, we usually have the case that the distance between, or the size of the slits is fairly large compared with a wavelength, say 50 times. It's hard to make really small slits, and wavelengths of light are very small. So in that case, this term here is going to be very small because the sink is small anytime the argument is more than 3 or 4 pi. So if A is much, much bigger than lambda, then A over lambda is much, much bigger than 1, say maybe 50. So then what this term here is 50 pi times sine theta. So if this is anything more than a tenth, then you're going to have essentially 5 pi, and the sinc of 5 pi is essentially 0. Let's go back up to this graph. The sinc squared, this is in terms of x over pi, so 5 pi is out here. It's really small. Even out here, it's already pretty small. Okay, so in that case, it's only really small angles, sine theta less than a tenth, that are going to be not zero. And in that case, we can use the small angle approximation. So I've drawn it I've drawn the geometry a little stretched out. You have the aperture over here, and the observation screen. They're separated by a distance L. Okay, and now this is the distance from the center out to where you're interested in. So again, we're thinking we want to know what the intensity is out here. So I measure the distance from the center. So x is this distance from the point you're interested in, the interference pattern, to the center. All right, so what we need is the sine. What we have naturally is the tangent. We know the distance from the screen to the observation screen, the aperture to the observation screen, and we know the distance from the central axis to the observation point. So that gives us the tangent. Now the nice thing is that for small angles, the sine and the tangent are the same thing. So we can just use the approximation that the sine of the angle is the tangent of the angle, which is just the things that are easy to measure, x and L. If you're in doubt at all, just try it out. So suppose x over L was a tenth. So x is 10 centimeters and L is a meter. Then to calculate the angle, we take the inverse tangent of a tenth, because we know the tangent is x over L. And then to get the sine, we take the sine of that inverse tangent. So if you do that, you find that you get something very close to x over L. It's off by 5%. So the moral of the story is, if x is less than a tenth, x over L is less than a tenth, then we simplify our equation. Okay, so that got rid of the extra sine inside of there, which made it look weird because you have cosine squared of a sine. It makes it look scary. I haven't really accomplished a lot, but this is a little more direct. Now we'd like to see some of the patterns here in this equation. The first thing we're going to look at here is the local maxima. So every place there's one of these maxima here, the bright spots. Okay, some of them are brighter than others, but I'm just talking about the location of the bright spots. Now that's due to this term here. And if you think, when is the cosine squared big? Well, that's when the cosine is either 1 or minus 1. The square makes it, the minus go away. So, and when is the cosine plus or minus 1? Well, that's when the argument is a multiple of pi. So we end up with this guy down here. Okay, so you don't need to memorize that. You just need to remember how trig functions work. Okay, because it's really just directly from the argument of the cosine. Okay, so where are they? The nice thing is that now you can just count. Okay, so m equals 0, well, that's when x is 0, right? That's the center. Okay, so the central maximum must be m equals 0. And then if you just go out from there, you get m equals 1, m equals 2, m equals 3. You can go all the way out here to m equals 24. Or over to the left, m equals minus 10. Now, we can do the same thing for the sink term. The difference is that while over here the simple thing is the maximum, over here the simple thing is the minimum, because the sign, which is in the numerator of the sink, has zeros when the argument is a multiple of pi. So we have the same pattern, but it gives the minimum. So the minimums here are these places where the intensity drops. Okay. The one exception is that the 0 pi isn't a minimum. Again, the sink goes to 1 at that point, so we can't have 0, the integer 0. Okay, so that's how to recognize these patterns in here. So this would allow you to look at this pattern and determine A and D. So if you measured the distance from here out to the 24th maximum, you know that m is 24. And you've determined what x is. So if you know the wavelength of light you're using, and you knew how far away the screen was from the slit, you'd know everything in here except D. So that's sort of the plan. I've written this up, and it'll be on the web page to do the lab. So I've taken those same images and overlaid a ruler in centimeters. This photograph was taken with the slits illuminated with a green laser that has a wavelength of about 532 nanometers. And the screen was 100 centimeters away from the slits. So with that information and these two images, you should be able to determine the slit width, but also for the double slit, you should be able to determine the distance between the two slits. Okay, and again, that's just by using these observations about where the minima and maxima are in the interference pattern.